Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Mukris bin Mazlan. I'm here to present on my progress report for this semester. We will start with the recap of what we've done for the previous semesters, as well as some of the things that should be highlighted. And then we're going to be following up with the current events of this semester. The thesis of my research is the development of a novel fixed-wing multi-rotor hybrid agriculture drone, the background of which is an agriculture UAV, in which case we are developing it to provide a means for the agriculture sector. The new design, or the novel design, is a combination of a fixed-wing aircraft and a multi-rotor drone, with the exception of not having any control surfaces. The context of the project is to allow for the development of this UAV to make it easier for farmers to use, to reduce the cost of it, of developing a UAV in the industry, as well as to improve on the methods in agriculture. The objectives are as follows: to investigate the flying quality and the stability of the fixed-wing multi-rotor hybrid using the simulation as well as the prototype, synthesizing a suitable control method augmentations once the flight simulation and the prototype have been scrutinized and as well as compared to, and to evaluate the flying quality using that control method augmentation. The methodology and data collection is already previously presented in the last video, but just a recap for everything. We are using Explain 11, a flight simulation program, as well as a designing platform of which we can design the aircraft and then put it into the trials in simulation. This is what it looks like in the simulated software. Essentially, it is a very basic 3D model of which it behaves according towards the specification we give it. And this is a screenshot of what it is going to be look like in the flight simulator software and the data output. As you can see, the data output happens in real time, after which we can extract the data and then we can extrapolate its flying quality. Of course, this has already been said in my last video. So again, these are the milestones of which breakthrough that happened last semester, of which we found a method to extract the data from the flight simulation to provide these graphs to show its flying stability in a simulated manner. As well as to point out that we can also mathematically describe the aircraft stability using common flight stability formulas. Basically, these are the short period and the long period calculations, similar to what a real aircraft flying today used to evaluate its flying capability without um, without having to fly it for real. Just to breeze through all of these data discussions that we provide essentially give it a way for us to know its stability in this simulated manner so that it can be compared to with the actual aircraft prototype. So now, what have we done for this current semester that we have been progressing in the research? So essentially, the simulation part has already been done. We have a method for it. We have extrapolated the data, and we know more or less how it kind of behaves in a similar environment to Malaysia's climate, as well as its ability to kind of maneuver in 3D space. Now, the purpose of it is always to compare it to the actual thing of which this method was thought up. Basically, I took the design from the X-Plane 11 flight simulator software, transferred it into AutoCAD, in this case CATIA or SolidWorks, and then transfer that into a 3D printing software, of which I will 3D print the parts into pieces and assemble them concurrently. So essentially, from model to prototype, we start with the X-Plane 11 plane maker, which is where we design the outer kind of shell of the prototype, how it kind of looks like, and we transfer that into a CAD software like SolidWorks, where we put in the different parts of which to join, maybe holes for us to put in screws, cavities where we can put our wiring, etc., etc. And then we break it up, put it into a 3D printing software, and then we essentially just 3D print the parts. Once 3D printed, we can assemble them. More or less, these are the things that usually takes the most time, which is to kind of make sure that the 3D printing process turns out with a good product and a good surface. Essentially, these are pictures of the early stages of the 3D printing process, where you can see it's not that good of a surface, and this uh, is further improved upon up until we can get our finished product. So this is what the prototype looks like after it's been freshly 3D printed and assembled. As you can see in the pictures, this is me essentially putting on the epoxy around the 3D printed aircraft to make it a little bit more sturdier. In the picture in this very center at the top there, you can see me measuring. So that is very important because we want it to be up into a scale where we can put in parts that we have essentially bought and are using to make the prototype fly. Of course, this is more or less a proof of concept of which will be compared to the flight simulation if it behaves about the same as the simulation or not. And that is essentially the purpose of my research, right? So essentially, the internal part of the system is a very simple kind of setup. Basically, we have a controller, the Pixahawk. We have a motor, a battery, of course. We have a controller, radio controlled, and we have ESCs to control the motors. For now, this is the setup that I have decided on. I will be adding more, for example, GPS, Bluetooth, maybe Wi-Fi. This would help to basically help with the control, as well as the third objective, which is to provide more sensors, more control to develop a more cohesive uh, controlling control method augmentation for this aircraft. Right now, this is what it looks like. I haven't really finished the wiring yet, but the aircraft itself has already been 3D printed. Has already been painted. Only what's left is this wiring, and then afterwards we can move on into essentially flying the proof of concept and see how it behaves. The data collection is used with Pixahawk. It allows me to kind of get a somewhat of a similar data output as the simulation, of which I can essentially just compare it apples to oranges, apple to apples, makes it easier for me to kind of like evaluate later on. So as you can see in my Gantt chart, the current state is right at the edge of August 2023. Essentially, we are on schedule. I plan to finish this prototype as well as write my thesis soon later. Thank you.